Yeah, good morning, Marta. Good morning, everyone. Let me share. I think I share my entire desktop. I think it's safer. Can you see my screen?
Yeah, we can see the entire desktop. Yeah.
And, I can go full screen. Does it look good?
Yeah. What I'm going to do, I'm going to give you a warning by putting a message on the slides that you have 2 minutes left. Okay, so right. I don't interrupt your presentation.
Yeah. So, should we start? Or
we can afford to wait a minute for everybody to show up.
Fine.
Hi, Andreas.
Hi, Umberto.
So long time we don't see each other. Sorry, yeah?
Yes, yes.
I switch off.
Happy to see you after many years. Hi.
So some instructions for all the speakers. Your talks are 15 minutes. I will give you a warning at the 2-minute mark. We will have 3 minutes for questions. For the audience, you can either raise your hand or put the question in the chat if you are unable to ask a question. And note that this time it's strict. We have another session starting at 10 using the same Zoom link, and we are very strict with time today. Okay, having said that, let's start with the first talk by Andreas Metz on understanding the proton mass in QCD. Andreas, the floor is yours.
Yeah. Thank you, Marta. Yeah, let's get started. So here's the outline of the talk. I will start with a brief motivation, then I move on to the energy momentum tensor, which typically underlies any mass decomposition of the proton or hadrons, and the renormalization of the energy momentum tensor. Then I will discuss a few different mass decompositions or sum rules and come to the corresponding numerics towards the end, if time permits. And this presentation is largely based on these two papers here. So to get started, the community has actually for decades looked at the decomposition of the proton spin with different incarnations of spin sum rules. In comparison, we have less work seen for the mass sum rule. Nevertheless, in the meantime, different mass sum rules are on the market. Natural questions are, how do they compare to each other? One question that bothered us, what is the impact of recent developments concerning the renormalization of the energy momentum tensor by those people here? And to sum this up here, important questions concerning the mass decomposition. What are mathematically valid mass sum rules? Is there an optimal mass sum rule based on the physics interpretation of the various terms? And what are the operator expressions of the various terms in the mass sum rules? Those two questions here in red are currently still under debate. So somehow doesn't move forward here. So let's start with the energy momentum tensor. We are interested in the symmetric energy momentum tensor of QCD, which has a quark and a gluon contribution. Quark contribution given here contains a covariant derivative. The gluon contribution is defined. So the field strength tensor. Relevant for the following is this here, the interpretation of the components of the energy momentum tensor on the main diagonal. T00 has a meaning of the energy density, while Txx, Tyy, and Tzz describe pressure terms. Because of that, if you look at the trace of the energy momentum tensor, you have a mixture of energy and pressure terms. Let me move on to the renormalization of the energy momentum tensor. And here I basically draw from recent work by Hatta, Rajan, and Tanaka. The total energy momentum tensor, because it's conserved, it's not renormalized, but the individual quark and gluon contributions are renormalized. And in fact, you have to look at operator mixing. Under renormalization, one has a total of 4 operators that mix. The energy momentum tensor is given by this linear combination of O1, O2, and O3. This is a pattern of the mixing equations. On the left-hand side, we have the renormalized operators. On the right-hand side, we have linear combinations of pair operators and renormalization constants. Let me move on to the famous trace of the energy momentum tensor. It has a classic term, which is just given by the quark mass term m psi bar psi. And then the famous trace anomaly here in red is generated by quantum loop corrections. Here, gamma m is the anomalous dimension associated with the renormalization of the quark mass. Beta is a QCD beta function. Now, the recent work by Hatta and co-workers is particularly relevant when we try to decompose the trace of the energy momentum tensor into quark and gluon contributions, which are given here. That's a quark contribution, that's a gluon contribution. In general, those contributions contain 2 parameters, denoted here by x and y, and they are related to finite parts of certain renormalization constants. Fixing those x and y corresponds to choosing a renormalization scheme. In the literature, different schemes have been proposed. We proposed, so there's MS type schemes. We proposed also so-called diagonal schemes, to which I come back in a moment. So let me now come to the relation of the energy momentum tensor and the proton mass. For this, we look at forward matrix elements. First, for the total energy momentum tensor, let's say for a proton characterized by a 4 momentum P, that matrix element is proportional to P nu. The number here in front depends on how you normalize your state. We can do the same thing for the individual quark and gluon contributions, and we get slightly more complicated expressions written down here. We have again a P nu term that is multiplied with a gravitational form factor A, either for quarks or gluons at 0 momentum transfer. And then there's a second term proportional to G mu, and that is determined by the so-called C bar form factor. Those 2 form factors have to satisfy those sum rules. Therefore, in the forward limit, the energy momentum tensor is actually fully determined by just 2 independent form factors. And as a result of this, any mass sum rule for the proton is related to at most 2 independent numbers. If we look at the trace here of the energy momentum tensor, take the trace here, then we get just 2m squared. Likewise, if we look at the 0,0 component, in the rest frame, we have also 2m squared. This can be written in the following way. Either the expectation value of the trace gives m, where this little n here is in our normalization of the state is 1 over 2m. Likewise, the expectation value of T00 gives m. This can be written in a more appealing way. If we integrate the 0,0 component over the space, we get the QCD Hamiltonian. And then one arrives actually at this equation here, which does not depend on how you normalize your state. That equation is equivalent to that one. In the following, I will mostly use this notation here. This is a lowercase n because it's a little more compact. The mass sum rules that I'm going to discuss are either decompositions of the trace or of T00 into quark and gluon parts. So let me start first with the so-called 2-term sum rule by Hatta, Rajan, and Tanaka. They decompose the trace of the energy momentum tensor in the quark and the gluon contribution that we saw a moment ago. The operators are given here. The quark contribution I denote by m bar q, the gluon m bar g. And these are these quark and gluon contributions in these what we call diagonal D1 and D2 schemes. That's one way of decomposing things. Another way here that was proposed a few years ago by Lorset, you decompose T00 into the quark contribution and the gluon contribution, quark and gluon energies. The operators I will show in a moment. Let me look at those energies expressed in terms of those form factors. The energies for both quarks and gluons are essentially the A plus C bar form factor. In contrast, the quark and gluon contributions to the trace are given by A plus 4 C bar. So obviously for the individual partons, we have different values for the energies and the contributions to the trace. Put differently, the M bar I are mixtures of energy terms, which are given by A plus C bar, and pressure terms, which are described essentially by the C bar form factors. Summing over quarks and gluons, I get, of course, the same result because the C bar form factor satisfies this sum rule. And let me finish with a trivial statement. Those two-term sum rules have one independent term only. If you know, for instance, Q, you know UG and vice versa. Let me now move on to the four-term sum rule by G and how we modified that in our recent work. These are pioneering papers here by G dating back more than 20 years. So his sum rule is based on a decomposition of the 0,0 component first into traceless and trace parts, and then further decomposing into quark and gluon contributions. So this decomposition is shown here. Here's a definition of the trace part, and that unambiguously fixes then what you would call traceless part in this way here. And now if we decompose the traces and the trace parts for the 0,0 components into quark and gluon parts, in our work, we found these expressions for the corresponding operators. If you sum over all these four terms, you get the nucleon mass. In the same manner as what we said related to the decomposition of the trace of the energy momentum tensor, those terms here in general describe mixtures of energy and pressure terms, as pointed out already a few years ago. So on top of this, this looks pretty ugly, and one guiding principle for our work was to get simpler operators by forming suitable linear combinations. Let me just guide you to the final result. We ended up with what we called actually a modified G sum rule, which has three terms. The first one is a quark kinetic plus potential energy. The second term is a quark mass term, and the third term is what we call the gluon energy. So we have three non-trivial terms only. The sum rule has two independent terms, and the reshuffling we did to get to these simple operators essentially removes this issue with mixture of pressure terms and energy terms. A couple of words on the relation to G's original work. G in his original work had these four terms. The difference is exactly 1/4 of the trace anomaly. There's different ways of looking at where the mismatch is coming from. Either it's due to a difference in the computation of the traceless part, or it's due to a difference in the meaning of some operators, as has been argued recently here. Just to give one example, what G and Liu in their recent papers call 1/2 E squared plus B squared, if I may go back for a moment here, in our notation would actually be this ugly looking expression. So let me also briefly compare this Lorcé's two-term decomposition. Actually, it's very similar. The gluon term, the gluon energy is the same. And for the quark, he has a total quark energy, and that is just the sum of the quark mass term and the quark kinetic plus potential energy. Put differently, our three-term modified G sum rule is just a refinement of Lorcé's two-term decomposition. To summarize this here, I'm looking in the following at three sum rules. The one is a two-term decomposition of the trace, which in the D2 scheme looks like that. We have two terms, the quark contribution to the trace, the gluon contribution to the trace. Both terms are actually not renormalized, they are scale independent. Then we have a two-term decomposition of T00, total quark energy, total gluon energy. Both terms are scale dependent. And finally, our modified G sum rule, where we split these here into two terms. We think this makes a lot of sense because this quark mass term is scale independent, and it has been studied in various approaches, including lattice QCD. So let me move on and say a few words about the numerics. We need two independent numbers as an input. One of them we get from momentum fractions of unpolarized PDFs for quarks and gluons. They are related to the traceless operators. There's only one independent number because both satisfy this sum rule. The second input comes through the parameter B, which is related to the quark mass term. As an example here, the modified G sum rule expressed through this AI and B looks like that. And the potential dependence on the order and perturbation theory that we're looking at and the renormalization scheme comes in through gamma M, beta, X, and Y. Moving on to the input that we take for those A and B parameters, we take these parton momentum fractions from the CTEC parameterization, and we take the quark mass terms from the sigma terms for light quarks, up, down, strange, and we also include charm. More specifically, we have two scenarios. In scenario A, we take the up, down, and strange quark mass terms from chiral perturbation theory. In scenario B, we take results from lattice QCD, where we include UD, strange, and charm. The main difference between the two scenarios is whether or not you include charm, because the charm sigma term is pretty large. So in the last 1 or 2 minutes, let me just show a few numbers here. First, let me discuss the scheme dependence for the modified G sum rule. We look at different schemes, MS, two incarnations of MS bar, and the diagonal schemes, scenario A, scenario B here for the 3 terms. And the quark mass term is not affected by the scheme dependence because it's not renormalized, but the quark and the gluon energies have a considerable scheme dependence. Similar qualitative features show up for the other sum rules. Of course, the scheme dependence is not something that is new to our community. Very quickly about the Hatta, Raban, Tanaka decomposition of the trace. We study the dependence on the order and perturbation theory, and if you look at those numbers here, there's a very mild dependence on this. This is a general feature actually for all terms and all sum rules. Moreover, depending on which scenario you take for the quark mass term, the quark contribution to the trace might become negative. Here's numerics for Lorcé's decomposition. Let me just focus here on these numbers. Here, comparing the quark and the gluon energies. Roughly speaking, the quark and the gluon energies contribute equally to the proton mass. And the last slide before I conclude, some numerics for this 3-term decomposition. Let's just compare here the quark kinetic plus potential energy with the quark mass term. So the quark kinetic and potential energy dominates over the quark mass term. That is less pronounced if we include charm in the quark mass term. One further remark on the quark mass term, because that is typically associated with the Higgs mechanism. In scenario A, this makes up about 8%. If we include charm, it's about 20% of the proton mass. Those numbers are much larger than the 1% that is frequently seen in the literature as attributed to the Higgs mechanism and the proton mass. So let me summarize. I'm not going through all the points here. Without intending to do so, we arrived actually at the 3-term sum rule, where we think all the terms have a clean interpretation. Our sum rule can be considered a refinement of a 2-term decomposition by Lorcé. Couple of remarks on G's original 4-term decomposition. Our work does not affect any of the existing phenomenology related to this decomposition. We just can't fully reproduce the operator definitions of this decomposition. And finally, and that's really a point I would like to emphasize concerning the phenomenology of the sum rules, the form factors AI and C bar I are largely known. And that implies no matter what preference for sum rule you have, the phenomenology of the mass sum rules is largely fixed. And in that regard, there's a qualitative difference related to the spin sum rule. Yet, and there's a lot of activity going on here, measuring the trace anomaly, in particular the F-squared operator, is still useful because it gives new independent input, especially for the C-bar form factor for gluons. Thank you. Sorry, I was going a little over. Sorry about that.
Thank you, Andreas. Any questions? Andreas, you mentioned that the three-term sum rule, it has a clear interpretation. Yeah. Is there a clear answer to which decomposition of the ones that are available it's more natural to consider?
Well, okay. I mean, as I said, this is still under discussion right now. It's one of these two questions that I put in red. Let me briefly come back to the interpretation. I mean, no one would argue that the quark mass term by itself, it's a meaningful term to consider. It's a separate contribution. And then we say, let's look at the nucleon at rest. And let's now look at the quark contribution to the energy for nucleon at rest and the gluon contribution. And then these are these quantities. So I don't think that actually the other decompositions which highlight terms that are related to measurements in deep inelastic scattering have a more natural interpretation in the context of a nucleon that you put at rest. So, well, I want to be careful here, but actually, maybe I'm biased. I consider this now from the point of view of interpretation of the terms, perhaps the best that is on the market. But I know other people have different opinions on that.
Thank you, Andreas. Yoshitaka?
Yes, so what do you mean by you didn't reproduce cheese operators, the last comment? I thought you saw the operators, no?
So, sorry?
What do you mean by you could not reproduce cheese
So yeah, I mean, so what Shandong and Liu are actually saying is specifically, if you look at the operator associated with the traceless contribution for the gluon, you can just call it 1/2 E squared plus B squared. And we think that at least in dimensional regularization, that is not straightforward, to say it mildly.
They did not show the trace part explicitly, but you can write it down, right? So this is the operator. Well, it depends on the scheme. But...
I mean, you can perhaps in particular regularization schemes.
Yes, it depends on the
lattice. If you look at lattice regularization, for which actually the trace is actually an issue, but in DIMREG, I cannot see how you can get there. Because what we call E squared and B squared, these terms have a meaning defined through components of F mu nu, and it's not fully at your disposal what you call 1/2 E squared plus B squared.
I'm afraid we have to move on. Please feel free to continue this discussion on chat, or after the session is over, there is a small break, you can continue this. Let's move on to the second talk of the day. Thank you, Andreas, again. The second speaker is Paweł Sznajder, who is going to talk about the phenomenological assessment of the proton mechanical properties from DVCS data. Paweł, you may start.
Can you hear me and see my slides?
Yes, we can hear you and see your slides.
Great, thank you. Yeah, so let me start immediately. This work is done in collaboration with people specified here. Right, this is outline of my talk. I will start with a very brief introduction, and then I will say a few words about extraction of DVCS Compton form factors. This is related to this work here, and this will be input to our other work, which is summarized by this paper, which was published at the beginning of this week. So this is a very fresh material, and it is about extraction of mechanical properties. So GPDs were mentioned several times during this conference already. So let me just remind you that these are three-dimensional objects telling you about internal structure of hadrons. These are functions of psi, x, psi, and t variables, and there is really a lot of those objects. Each of them is defined either for a specific quark flavor or for gluons. We want to study GPDs because they give access to information about spatial distribution of partons. This is the so-called nucleon tomography. But also GPDs, and this is an absolutely unique feature, they give access to energy momentum tensor form factor, or in general to the energy momentum tensor. Here it is parameterized as a function of 5 energy momentum tensor form factors, A, B, C, and D and C bar, and those can be accessed in the GPT formalism. We are interested in this combination of those form factors accessed in GPD formalism in this way. This is known as the G-sum rule, and it gives information about total angular momentum, which can be used to tell us, well, it tells us something about the nucleon spin decomposition. But also because in GPD formalism, nucleon is seen as a three-dimensional object, we can also study its mechanical properties, like for other three-dimensional extended objects. And here the key object is this energy momentum form factor C. And my talk and this analysis that I'm going to present today is about extraction of this form factor from experimental data. Now, GPDs are studied in many processes, and we are trying to extract them using as many observables as possible in a broad kinematic range. And this is really required because these are three-dimensional objects. So we need to cover the whole phase space. And in addition, we have a lot of those objects. So we need tools to distinguish between contributions coming from various GPDs. And for that, we are using various experimental setups and various processes. And today I will focus on a DVCS, which is considered to be the golden channel to study generalized parton distribution. And in addition, we already have some data for this channel. So the first step in this analysis is the extraction of the so-called Compton form factors. Compton form factors are DVCS subamplitudes. And you may think about them as the most basic observables as one can ambiguously extract from experimental data. So in this analysis, we are extract those Compton form factors from world data on the DVCS and proton target. And we are extracting those CFFs using artificial neural network approach, which means that we are basically completely reducing model dependency of this extraction. There are many features of our analysis. I don't have time to discuss them in details, but let me just say that what stands, well, our analysis stands out because we independently parameterize either real, well, both real and imaginary parts of Compton form factors. We are not using any power behavior prefactors, and we are making a very careful propagation of experimental uncertainties using the so-called replica method. So this slide tells you something about the quality of our fit and used data. So we are using data coming from class Hall A, Hermes, Compass, Zeus, and H1. And the quality of fit is really satisfactory. These two plots show you the coverage of phase space by used data. And also you have the indication of some cuts that we are using really to restrict this analysis to region where we believe that leading twist and perturbative description works. On the left-hand side, on this slide, you can see some class and Hermes data and a result of our fits indicated by the gray band. And on the right-hand side, you can see the parameterizations of Compton form factors, real and imaginary parts. And this is really the outcome of this analysis here compared with our previous extraction and with some GPD models. So now the next step towards the extraction of those mechanical properties is the evaluation of the so-called subtraction constant. So the subtraction constant appears in the dispersion relation where we have integral over imaginary part of Compton form factors, but we also need a real part of Compton form factors. So we have, as a result of our analysis, parameterizations for both real imaginary of H and imaginary of, part of H. So using this relation, we can evaluate a subtraction constant, which is shown here. And this will be the input to our new analysis. Now, at this moment, it is really crucial to understand that what we have now is basically a refined information coming from experimental data. So we take data coming from all experiments that took DVCS data, many types of observables, asymmetries, differences of asymmetries, cross sections, asymmetries, and so on, and we refine them to get this information about subtraction constant. And because our analysis is model independent, those plots really summarize our knowledge of subtraction constant that we currently have from experimental data, and there is no model dependency here. So now let me show you the link between subtraction constant and energy momentum tensor form factor C. So dispersion relation, you know, here we have this subtraction constant, and in GPD formalism, this subtraction constant can be related to the so-called D term. So here you can see the relation for leading order coefficient functions. This D term can be then decomposed into a set of Gegenbauer polynomials shown here, and it is important to recognize that those parameters of this extraction, this D parameters evolve independently. So this will be our tool to distinguish between contributions coming from various Ds. So finally, we have this relation, and the last part, the missing part of the puzzle is this relation where we can relate this energy momentum tensor form factor C with this first element of this Gegenbauer extraction. So I will show you the extraction of this D1, but you may think of it basically it is equivalent to this energy momentum tensor modulo this factor 5. So this is relatively a clean path how to extract this energy momentum tensor form factor. We have parameterizations of form factors and we have those formula, but now let us confront them with the reality. So this is our master formula, and we to really extract this D1, we need to make several approximations or simplifications. And we do them in this analysis, and basically this is one of goals of this analysis to really specify those assumptions and to discuss consequences of those assumptions on the extraction of D1, because those assumptions are commonly used in this field of research. So the first thing that we need to do is to restrict this integral. So we cannot integral between 0 and 1. Well, if you know dispersion relation written in the new variable, you know that you need to integrate between some minimal value of nu and infinity. We don't have, of course, data for nu equals infinity, which means psi equals 0. So we need to restrict this integration, which we do, and we check that this is not really a problem. then you need a good knowledge of both real and imaginary parts, and it's really important that you need to know this imaginary part in as broad a range as possible. This is information for us that this D term, or this energy momentum tensor form factor C, simply cannot be extracted in a single experiment. You need really a global experimental effort to extract it, because you need to have a knowledge of quantum form factor basically in the whole available phase space. So this is about the left-hand side of this equation. Now let me talk about right-hand side of this equation. So here we have sum over quarks and infinite sum over this Gegenbauer terms. So of course we need to make some truncation, and usually this analysis and in all other phenomenological analysis, people just leave the first element of this in this sum. This is justified for large values of q square because of the evolution. So all other d elements, d3, d5, and so on, they die out with q square. Only d1 survives for q square equals infinity, basically. So this justification seems to work well for large values of q square, but for instance, at the JLab, it will not work very well. But this is something that we are still using. Then leading order DVCS do not probe gluons explicitly, but implicitly we have sensitivity to gluon contribution via evolution. So if we want to study the gluon the evolution of this D, we need to have to assume something about gluons. In this analysis, we assume that there is no gluon contribution at some very, very low scale, and we radiatively generate gluon contributions. Because we are considering only proton data, we are not able to distinguish between various quark flavors. So we assume that there is a symmetry between those quark flavors. And finally, we need to say something about T dependence. And here we are using the so-called triple ansatz, and I will show you later some consequences about this. Right, so this is the effect of our analysis. So here you can see again, the gray band is the artificial network analysis. So here this is the subtraction constant extracted really independently, and the gray and the green band represents the situation when you extract subtraction constant using all those previous simplifications and assumptions that I listed at the previous slide. So here you can really see the effect of those simplifications. So in this analysis, well, you see the effect of the simplifications, but at the same time, this simplifications allows you, at least now, because of this sparsity of data, to extract, for instance, D1, and here you can see the results that we obtained, and here the comparison with other extractions and with some theoretical predictions as a function of q square. So our extraction is represented by the green band. This is, for instance, the point of the extraction obtained by Krzeszimir, and somewhere here is also the point obtained by François Xavier and his collaborators. So the point here is that we may argue about methods and the details of neural network analysis, but in both our and Krzezimir's analysis, it seems that at this moment we are just not able to say anything about this D. I mean, we cannot conclude that it is different than 0. In this analysis, we were also trying to extract D1 and D3 all together, but because of the quality of data and the available range of Q-square, we were not able to do that. So basically, the correlation is so strong that you can fit any two values that you want, and this is shown in this correlation plot. So we definitely need better data and longer arm in Q-square, and we hope that this will be provided by EIC. And this is the last one of the last slides. So here we discuss the consequences of our choice of T distribution, T dependence. So as I mentioned, we are using the tripole ansatz, and you may pose a question: what is really the effect of those parameters that we choose? If, for instance, if you take alpha equals 3 or alpha equals 4 or 3.5, does it make any difference on the profile of the pressure? And it turns out that it makes really an enormous difference. So here you can see, for instance, the various curves for various values of alpha, and please note that here you have the logarithmic scale. So even if you extract those parameters from experimental data with some uncertainties, then anyway the extraction of profiles will be really difficult. So to conclude, our analysis demonstrates really common approximation and their impact, shows status of the extraction of D1, demonstrates evolution effects, and much more. And the most important is that really provides a benchmark for this kind of analysis for the future. That's all. Thank you.
Thank you, Paweł. Any questions? We have time for one quick question. Can you, yes, go ahead.
What's your argument behind the assumption that D1 strength is equal to D1 up and down?
Sorry, I must say we do not have a really strong arguments for that. This is something that we just assumed. I know that in some analysis, people take either U equals D equals S, but in other analysis, people take U equals D and S equals 0. This is just choice that we made, but I don't think that we have any strong arguments to do that.
Well, there is actually an argument from large NC that this is a flavor independent, but for strangeness, it's a bit tricky, of course. Okay, thanks.
But yeah. This is something that we really discussed, and yeah, this is a strong assumptions. Possibly by taking data on well, not really neutron, but I hope that maybe if we start to include data coming from mesons, something could be said about this.
Thank you, Paweł. Let's move on to the next presentation. Our next speaker is Sreeraj Nair, who is going to talk about the mechanical properties of the proton in a light from quark-diquark model.
Hello. Are you able to hear me?
Yes.
Okay. Firstly, I thank the organizer for this opportunity. And today I will discuss about the gravitational form factors and the mechanical properties of proton. Let's see the outline here. My talk is mainly divided into two parts. The first part, which is a longer part, I will discuss our work on the gravitational form factors in the quark-diquark model, and I will show you the results. And in the second shorter part, which is an ongoing work, I will discuss the gravitational form factors in the basis light front quantization approach. And finally, I will conclude. Okay, so let's move on. So let's quickly look at the light front quark-diquark model. So here our aim is to have a two-body problem instead of a three-body problem. So we have a single quark and a scalar diquark state in this particular model, and the wave functions are constructed from the ADS QCD correspondence in the soft-wall model, and the light front wave functions are as shown here, and the detailed wave functions for different spin configuration is as follows. And the modified soft-wall wave function for two-particle bound state will be as shown here. And in this particular approach, we will use kappa equal to 0.4, which is inspired by the fact that it gives excellent results for the electromagnetic form factors for this particular value of kappa. Okay, so let us quickly again look at this parameterization for the energy momentum tensor here. For the symmetric energy momentum tensor, you can have this parameterization in terms of this four gravitational form factors, A, B, C, and C bar. And in this particular model, we will calculate all of these four gravitational form factors. Let's see. So we consider free quark inside the proton, and we observe that these are the different components of the energy momentum tensor that can be used to extract these gravitational form factors. For example, the plus component will give you A and B depending upon the helicity flip and non-flip. So A is for the helicity non-flip, and B will come when there is helicity flip between the initial and final proton state. And the minus perp component together with the plus minus component can help you extract C and C bar form factors. So we calculate all of these components of the energy momentum tensor in the quark-diquark model and extract these four form factors. So here I just show you the final analytical result that we get for all of the four form factors in terms of the integral, which are further calculated numerically. So here we see that, for example, if you focus on the C form factor, the C form factor has this 1 over q square term sitting outside, which causes a divergence at q square exactly equal to 0. So which I will come to again later, how to deal with that. So before that, let's look at the results for A and B. So these are our results for A and B for U plus D. So here we see that the green curve is at the initial scale, and then we perform an evolution up to a final scale of 4 GeV square. And there are results for two evolutions with different initial scales. This is just to show how the initial scale affects the result. From the result, we can see that the result with the lower initial scale, that is 0.32, is in agreement with the lattice results. And on the right, again, we see the B gravitational form factor, which for U plus D is nearly equal to 0. And so we see that these results are consistent with the lattice results. So now let us look at the result for D form factor here, the D term. The D term is related to the C by this factor 4. So here I'm showing you the results. On the right, it is just a zoomed version of the left plot. So we have compared it with various available results from theoretical models as well as the lattice results. Again, this has been plotted from the x-axis does not start from 0; it starts from 0.1. Since at exactly equal to 0, we have this pole, which comes from the analytical calculation. So what we do is that we can do a fit for the we can do a fit at higher q square range, and then we can extrapolate back to q square value, q square equal to 0 value. And also we see that qualitatively the behavior is in agreement with the lattice results. It is negative over the entire range of q square. And we find that this particular expression, this particular fit function can describe the data well over the region of Q square. And these are the fitting parameters that has been used. Okay, now the C bar form factor. These are the results for the C bar form factor. Again, this has been evolved for 2 different initial scale. And the band that you see is a band, is an error band with 2% error in the parameter model parameters. Here we see that on the right, the table shows you the C bar value at 0. So we can see that in our case, it agrees quite well with the asymptotic result. And also, and also the positive distribution decreases with the evolution. For example, if you see our results, they are not negative over the entire Q square region. There is a slight region over which it goes above 0. Yeah, so these are the results for all of the form factors. Now, since we have these form factors, we can look at the mechanical properties, which are particularly related to the D form factor. So here we can write the pressure and shear forces inside a nucleon, as shown here, where D tilde is just the Fourier transform of the D form factor in the P space. And again, the normal and tangential forces are again related to these pressure and shear forces, as shown here. So now we are in a position to calculate all of these mechanical properties. So I will directly show you the results for this. For example, here are the results for the pressure and shear distribution. So on the left, we have the pressure distribution. On the right, there is a shear distribution. Again, the bands are for 2% uncertainty in the model parameters. And again, we see that the overall behavior is in agreement with the results. And we see that, for example, on the left plot, we see that it will obey the stability condition, since you have this positive and negative regions for the pressure distribution. And similarly for the shear results we have. Now let me move on to the results for the force. So we can have like a tangential and a normal force for a spherical shell. And again, we see that on the left, the results for the normal, and on the right, it is for the tangential force. And you can see that for the tangential, it has a positive core, which is surrounded by this negative tail, I mean the attractive force. And again, the results are in qualitative agreement with the available experimental data. Okay, so now this concludes my first part. And in my second part, which is an ongoing work, we are again calculating the same quantities, I mean the gravitational form factors, using the basis light front quantization approach. Now this BLFQ approach is a non-perturbative approach in which we try to solve this eigenvalue equation numerically. And we consider the Fock space expansion for the proton state. And in this work, we are only focusing on the leading Fock sector. And the Hamiltonian that we will be using is shown here, which is an effective Hamiltonian, which has this, the kinetic energy part, and it has the confining part, the transverse confining part, confining potential, and the longitudinal confining potential, where the transverse one is inspired from the holographic soft wall model. And also we have the one-gluon exchange interaction for simulating the spin behavior. So with this effective Hamiltonian, we can calculate the wave functions numerically, and with the wave functions, we can calculate the energy momentum tensor. Again, we do that and we calculate the A and B form factors. It should be noted that this is a work in progress. So here you see these Nmax and Kmax term, they are the basis truncation parameters corresponding. For example, Kmax is the longitudinal basis truncation parameter, and Nmax is in the transverse direction. The results are expected to improve in the continuum limit, I mean, as you increase Nmax and Kmax. So here on the left, I show the results for A, for U quark, D quark, and the U plus D quark. Similarly for B, and the results are as you would expect them to be. Now let us move on to the longitudinal momentum density. So here what we do is that we calculate these momentum densities. For example, in this particular plot, you will see the momentum density in an unpolarized nucleon where the quarks are also unpolarized. So on the left, we see the contour plot for the U quark, and on the right it is for the D quark. And we see that there is this symmetry. And now we want to see how the spin of a transversely polarized nucleon would affect this symmetry. So if we now turn on the polarization, rho t here would capture this polarization effect, which is seen here. On the left, you will see that it is slightly shifted towards up in the U quarks, and on the right, for the D quark, we see that it is slightly shifted towards down. And this is more clear if we plot this for a particular fixed value of Bx, let's say, for example, 0.15 Fermi. And here we see that on the left, both are for the unpolarized, and on the right, it is for the transversely polarized case, where the nucleon is transversely polarized. We see that on the right, for the U quark, it is slightly shifted towards the right of the central zero line. And again, on the D quark, it is shifted towards the left. This is because the B form factor for D quark is negative. So this actually, now, this is again the final result that I have. This is for the D term that we have calculated. And here I only show the result for D quark, since this is an ongoing work. We are still calculating this for different Nmax and Kmax. Here we again, this is a fitted result. Again, we do it for the high Q square region, and then we extrapolate it back to zero value. So here it is just shown for the high Q square region, high Q square in the sense that not exactly starting from zero. And this actually concludes my talk. I will present the conclusion here. The conclusion is to say that we have calculated these form factors, gravitational form factors, in the light front quark-diquark model. And for all of them, we observe a qualitative agreement with the available results. We also calculated the mechanical properties. And currently we are, the work is in progress for calculating these form factors as well as the mechanical properties in the BLFQ approach. Thank you for listening.
Thank you, Sreeraj. Simone, you have a question?
Yes, thank you for the talk. And I was wondering, in light from quantization, you have a clear separation between dependent and independent degrees of freedom in the fermionic sector. So your quark field has a bed component, which is fully determined by the equation of motion. And if you confine yourself to T++, this is no issue. But if you go to T plus minus or other components, that becomes. So how do you treat that bed component?
You mean T minus perp component?
Yes, for example, minus perp or minus, I think, or minus plus, probably minus plus, as at least one bed component of the field, of the psi field. And that is a dependent component, and you cannot treat it as independent degrees of freedom. So how do you do not have gluons in this model, but that simply means that you have simpler equation of motions, but still.
Right. Yeah, we actually calculate this. I mean, the energy momentum tensor, the minus perp component. We don't have that kind of an issue that you are talking about. For example, which bad component are you talking about?
Okay, I think that the time is strict, so maybe we can discuss this later. Okay. I was talking about, for example, plus-minus component, but we can discuss this separately or whatever.
Okay.
Yes, that's a good idea. Any other questions can also be inserted in the chat. Thank you, Sreeraj, again. And let's move to the next talk by Kemal Tezgin, who is going to talk about the two-dimensional densities of the energy momentum tensor in a quark model.
Yeah, so I'm just opening.
Okay, you may start.
Okay, great. Welcome, everyone. The title of my talk is 2D densities densities of the energy momentum tensor in a quark model. And this is still an ongoing project with Cedric Dorset and Peter Schweitzer. So the matrix elements of the symmetric energy momentum tensor for a spin 1/2 hadron can be parameterized in terms of 4 form factors, here denoted by A, J, D, and C bar. So we have the average form momentum of the system, here denoted by capital P, and the momentum transfer to the system by delta, and the invariant momentum transfer by T. And because energy momentum tensor is a conserved quantity, this implies that the form factor C bar here, once it's summed over its constituents, should yield 0. On the other hand, the Poincare symmetry implies that the form factor A at T equals to 0 should yield 1. And actually, this is related to the fact that the quarks and gluons carry the 100% of the nucleon momentum, whereas the form factor J at T equals to 0 must yield 1/2. And this is related to the fact that quarks and gluons carry 100% of the nucleon spin. On the other hand, the other fundamental property of the nucleon, which is the so-called D term, which is related to the form factor D at T equals to 0, is an unconstrained, and it needs to be experimentally determined. Okay, so the first part of my talk will be to compute the energy momentum tensor form factors in BAG model. So BAG model describes the nucleon consisting of non-interacting quarks confined in a bag. So the Lagrangian of the model consists of 3 parts: the quark part, the surface contribution, and the bag contribution, which here we use the letter G to mimic the gluons, but there is no gluonic degrees of freedom in the model. And so B is the bag constant, which is the energy density inside the bag, which is a positive quantity, B here. And we call LG not for really gluons, as I said, but it actually mimics gluons of QCD in the sense that it is non-fermionic degree of freedom, and it is crucial also for the formation of bound states. So this is actually required for us to bond the quarks inside a bag, and they are non-interacting quarks inside the bag. So once you get the equations of motion, you get inside the bag, we have the free Dirac equation. And then on the surface, on the other hand, we have a linear boundary condition, which actually ensures you that there is no current flow out of the bag. So we have nu mu here, which is the 4 normal vector. So there is no current flow out of the surface. And the nonlinear boundary condition ensures you that the energy momentum tensor is conserved at the surface. So another thing we use, another method we use is the latency limit in our computations. So because coupling constant of QCD is not a good expansion parameter in the sense that it is not, it doesn't allow us to perform perturbative computations at all energies. In the literature, it has been discussed that the only known expansion parameter valid at all energies in QCD is actually 1/NC. Once we generalize the color gauge group SU3 to SU and C, where NC is a large quantity. In this picture, baryons appear as solitons of mesonic fields. And in the same work of Witten, it has been discussed that the nucleon mass actually scales with the number of colors while retaining a stable size. So it means that as we increase the number of colors in the model, we get denser and denser baryons. And this has some implications for the kinematic variables, and they are given in here. So latency behavior of the energy momentum tensor form factors has already been discussed in the literature, and we confirm those relations in our study. And then, of course, we take NC a large, so it says an infinite, okay, we take it to infinity, but in the end, once we compute the leading terms, we set NC equal to 3 to the real world case. So here, in our computations, also we use the symmetric quark energy momentum tensor as given in here. So we compute it by computing the canonical energy momentum tensor, and then we symmetrize it, because canonical energy momentum tensor is actually an antisymmetric one. And the contribution from the back is given in here. So in our previous work, we have computed the form factors A, J, D, and C bar for up plus down quarks. So we have only the quark contributions to the form factors here. And we compare our results with G et al., where G, Melnichuk, and Song in 1997, they actually gave the first model computations of the chiral even GPDs as well as the energy momentum tensor form factors. And but they didn't work on the large NC limits, so they have boost effects. So in the large NC limits, the nucleon is basically non-relativistic, but the quarks inside the nucleon can still be relativistic. And we compared our results with them. And then for the boost case, when the nucleon has a boost, we have definitely deviations from their results. But when we take no boost in their approach, large NC approximation is actually a very good approximation, and you only see a slight deviation for the form factor A only here. And another advantage of taking the large NC limit is that you don't have the relativistic corrections, and if you do not actually in a Lorentz invariant way, if you do not boost the system in a Lorentz invariant way, you actually might deviate from the constraints. So, for example, in G et al., because of that, there was the form factor J at t equals to 0 is not actually 0.5, which it should be. The physical information in the energy momentum tensor form factors are actually revealed in the bright frame. So what is bright frame? So there is no energy transfer to the system. So the momentum transfer is purely spatial, and it's a head-to-head collision. So the capital P, the trim moment of the capital P is 0. And then once we take the Fourier transform of the matrix elements of the energy momentum tensor with respect to delta, we get the 3D energy momentum densities. And the 0,0 component of this energy momentum density is related to the energy distribution inside the hadron. And then 0K is related to the spin. On the other hand, the spatial components, IK, are related to the mechanical properties of the nucleon. And here the relations with the mass, spin, and the D term are given in here. So Belinfanti improved, or the symmetric angular momentum density is given by this expression in here, and it can be decomposed into monopole and quadrupole terms. And these two terms are actually related to each other. So if you know the monopole contribution to the angular momentum density, you can actually generate the quadrupole term and vice versa. Similarly, the components of the Tij of the static stress tensor encode the information on the distribution of pressure and shear forces. So again, we have the monopole and the quadrupole contributions, and the shear forces are related to the distribution. SR is related to the distribution of shear forces, which is the off-diagonal terms, and PR distribution is the distribution of the pressure inside the hadron, which is related to the diagonal terms of this tensor. So again, in our previous work, we have computed the energy momentum tensor densities here. So we have the total contributions here by the red curve, and R1 is, okay, the back radius is at 1.7 femtometer. And we have the back contributions, which we here indicated by gluon, are only on the diagonal terms. So for the T00 and for the shear, for the pressure contributions. And we observe that the energy is mostly located near the center, whereas the angular momentum is towards the back boundary. Again, the same for the shear forces. And we have for the pressure, the following curve in here. This is an important result in the sense that the pressure must have a node for the following reason. The energy, pressure and shear forces are related by a differential equation is given in here, and Bragg model satisfies that. And this also implies that the stability condition must be satisfied, and the Bragg model actually satisfies this relation well. So here we have positive region and negative region, and they cancel each other and yield 0. On the other hand, we also have C bar up plus down quarks plus C bar, the back contribution actually yields us as well 0. Okay, so we have talked about the 3D distributions, and we said they are they can be revealed in bright frame. But actually, if we relax the condition of 3 momenta of P being equal to 0, we can actually talk about 2D EMT densities. So they are actually manifested in elastic frames. So again, there is no energy transfer to the system, so that the initial and final states are affected by the same Lorentz contraction. And this time we have P non-zero, but then we can choose basically delta perp to be non-zero, but delta Z become 0. And then once we take the Fourier transform of the energy momentum tensor matrix elements with the requirement that P perp and dz equals to 0, we actually get the 2D densities. But now they are also depending on a parameter Pz here. But for Pz equals, when it goes to 0, 2D distributions are actually related to the 3D distributions onto the transverse plane. So once you know the bright frame distributions, once you project them onto 2D space, you actually get the distributions in the elastic frame at Pz equal to 0. So we have computed those densities, but for this time for the asymmetric energy momentum tensor. So here, instead of the symmetric one, the antisymmetric tensor can be parameterized in terms of 5 form factors. And the additional form factor here given by S is related to the intrinsic spin of the system. So we have this time the kinetic quark energy momentum tensor operator, which is the canonical energy momentum tensor in our case. And this time we have not only one angular momentum density, but actually we have orbital angular momentum density plus the intrinsic spin contribution. Here we have the distributions given in here. So what I wanted to emphasize is that the orbital angular momentum contribution is leaning towards the back boundary again, whereas the spin contribution is more concentrated in the center. Here we have the Belinfante contribution, which is the result of the symmetric energy momentum tensor. And here we have Jz, which is the sum of these two contributions. And as you can see, the Belinfante one is leaning towards the back boundary again, whereas Jz is more concentrated in the center. So we have looked at these densities at certain limits. So here we have at fixed nucleon mass. So we have the proton mass here, and then we change the quark mass from 0 to 1/3, nearly 1/3 of the nucleon mass. So here MQ equals to 0 is the highly relativistic case. So the quarks are highly relativistic. Here we have highly non-relativistic quarks. So here we have the distributions of SC and Z and their sum with this curve here, T curve, and then we have the Belinfante contribution, which is the result again from the symmetric one. Here, what I wanted to emphasize is that again, the orbital angular momentum contribution and the Belinfante improved angular momentum distribution are more leaning towards the back boundary. And as you increase the quark masses, actually those contributions, the orbital angular momentum contribution actually vanishes. And then when you come nearly to the non-relativistic region, you get actually 0 orbital momentum contribution to the system. So here is the summary. Energy momentum tensor form factors and 3D densities are evaluated in the back model in the large chain C limit. And we have also discussed the energy momentum tensor 2D densities in the large chain C limit, and their various limits are discussed in this ongoing work. So the consistency of the model allows us to test many theoretical concepts in a lucid way. Thank you for listening.
Thank you, Kemal. Is there any question? We have time for one question. If something comes up, you can put it in the chat. Thank you, Kemal. And we can move on to the next talk. So our next speaker is William Focillon, and he's going to talk about the study of potential transverse momentum and potential angular momentum within the scalar diquark model.
Hi, hello, can you hear me?
Yes.
Okay, very good. So I'm sharing my screen at the moment. Okay. Can you see the screen now?
There is a green box half cutting your okay, now.
Okay. So you can't see the full screen. I'll try again. Sorry. Okay.
Okay.
Is that better?
Yes.
Okay, perfect. So hello, everyone. My name is William Focillon, and today I'm going to talk to you about the study of the potential transverse momentum and potential angular momentum within the scalar diquark model. So first of all, thank you for the organizers for inviting me. I'm very thankful. So I'm going to be presenting the work I did with the Andreas Metz Understanding and my PhD supervisor, Cédric Lorcy. So first of all, so in the proton, if we can formally write that the proton spin is decomposed between the spin of the quarks of the gluon and the orbital angular momentum, then experiments have shown that this spin is not only carried by the quarks, and so this is because we have to deal with a relativistic quantum system. And so even if the field of the nucleon spin has matured, we are still longing for a simple and intuitive understanding for what is, for example, the orbital angular momentum. So in this presentation, I'm going to talk to you first about the nuclear spin. Sorry, there's an S missing. So the nucleon spin decomposition, and define what we call, the transverse and angular momentum. Then to explain how we perhaps could have an intuitive understanding of the formation of orbital angular momentum. I'm going to first describe you the cyber shift and see how we can use that to maybe create a torque. And finally, so I'm going to look at both the potential transverse momentum and angular momentum within the framework of the standard, the scalar diquark model. So first, I'm going to recall the most commonly used spin decomposition. So both, G and Jaffe-Manoir decomposition. So first we have the G decomposition, which is kinetic decomposition and corresponds to the classical notion of orbital angular momentum. So every operator in the sum LQ plus SQ plus JG are a gauge invariant and can be measured. And we've got a local definition of the derivative. And then for the Jaffe-Manoir spin decomposition. We've got a decomposition in both quark and gluons, and again in both spin and orbital angular momentum. So it corresponds more to a canonical decomposition, and it highlights the light cone gauge. So we've got again a total decomposition in both quark and gluon spin and orbital angular momentum. However, not all of these operators are gauge invariant, and if one replaces the partial derivative by a non-local definition of the gauge covariant derivative, we can restore gauge invariance. Okay, so now with those definitions in mind, we define the potential transverse momentum and the potential orbital angular momentum as the difference between both of them in each of the framework. And with a bit of algebra, we can see that in the light cone gauge, we've got a very simple rewriting of what is both the transverse momentum and angular potential angular momentum. So it's shown at one loop in perturbation theory that LZ, so the potential angular momentum, vanished. However, lattice QCD showed that the Jaffe-Manoir orbital angular momentum was significantly enhanced compared to the G definition of the angular momentum. So we want to see if we can use one of the quantities shown on this slide to understand or to expect or estimate the other quantity. Very well. So now I'm going to talk a bit about the Sivers shift. So if we look at transverse momentum distribution, I've written the TMD correlator here in equation 3. We see that it makes use of a Wilson line in the middle, which is a path ordered integral of an exponential of the gluon field. And we've got a gamma path, which is very important. And so the Wilson line inside of the correlator, of course, makes the correlator a color gauge invariant. We see also that it encodes either final or initial state interaction. And what's very important is that the path used inside of the Wilson line is process dependent. So for example, if we talk about SIDIS or the Drellian process, we'll have in some ways opposite path to take into account in the Wilson line. And the Wilson line is at the origin of the breaking of naive time reversal symmetry. So with that in mind, if we write the TMD correlator, we can separate it between both the contribution from the unpolarized partial distribution F1, and we've got a contribution that comes from the so-called Sivers function. And we see after some algebra that we can directly relate the Sivers function to the potential transverse momentum by a simple integral. So the Sivers function is one of the two leading twist functions that are all under time reversal for a spin 1.5 target. And so we see that a non-zero Sivers function can lead to a non-zero transverse momentum if, of course, we see in equation 5 that the target polarization SK must be transverse. And analytically, we find that sorry, not analytically. So this Sivers function encodes the presence of final state interaction in CDIS and of initial state interaction in Drelian through gluon exchanges. So now that we have seen that a polarized, transversely polarized target can lead to a displacement of quarks in the transverse space, Burckhardt made the case for the following lensing mechanism. So the fact that we've got a displacement in the transverse space means so we've got a displaced distribution of unpolarized quarks in the transverse space. When we have this asymmetry created, then when the quark leaves the target, the gluon field will have attracting interactions with the selected quark, and so this will be opposite the direction of the struck quark, as we can see on the figure. And so with this proposed mechanism, we could link the displacement of unpolarized quarks in the transverse space to a torque of the target. And so, for example, there was an article in which Pasquini, Rodini, and Bacchetta showed that under restrictive conditions, such a lensing mechanism could be exhibited. So, with that in mind, we look at these quantities in the scalar diquark model. Okay, and so in this scalar diquark model, so the nucleon splits into both a quark and a scalar diquark structure. So if you want more details, there's a slide that exhibits the Lagrangian and the Feynman rules in this model. So we've got Lorentz covariance that's maintained, and we have charged quark and diquark, and the nucleon, which is on the left with the 3 bars on the figure, is not charged. So we're only going to look at 2 loops in this model. So the initial state and final state interactions will be considered as an abelian theory, because at 2 loops, the non-abelian nature of the theory will only appear at further loops. And this model provides interesting calculations for analytical results, and there are already a lot of results that are accessible in the literature. Okay, so without loss of generality, we restrict ourselves to the case of the light cone gauge with semi-inclusive, deeply analytic scattering process. And we use dimensional regularization to regularize the results. So we can show that the transverse momentum, so the potential transverse momentum, can easily be written in terms of a correlate, not a correlate, as these expressions in equation 6. And so we see that we've inserted 3 fields, so psi bar A and psi. And we see that this is general to all of the diagrams we calculate. So using symmetry, we can see that with any process, the G potential transverse momentum, sorry, the G transverse momentum has to be 0. However, the Jaffe-Manoir can have a contribution. And so we need a gluon or photon exchange to have a contribution. So without going in too much into details with the calculations, we calculate diagrams at 2 loops, which are always of the similar form. And so we can use conservation of momentum to show some results that always are useful, and symmetry as well. And so what's important is that we found a non-vanishing Sivers shift in the scalar diquark model that we can cross-check with known Sivers function. And so this calculation yields a result at order 1 over epsilon squared. And so now, if we have in mind the mechanism I've just described, if we calculate the same diagrams for the potential angular momentum, we find, in fact, that the potential angular momentum vanishes at that level. So the G and Jaffe-Manoir definitions of orbital angular momentum coincide at 2 loops in the SDM. And so in conclusion, to finish up quickly, so we calculated both the potential angular momentum and potential transverse momentum at 2 loop in the scalar diquark model. And we find the surprising result that the potential orbital angular momentum vanishes at order 1 over epsilon squared. And this puts in jeopardy the intuitive proposal of a lensing mechanism. And so for the future, we can perhaps look at a deeper perturbative calculation of the potential angular momentum. But what's more interesting would be to use the scalar diquark model as a chance, as a good model to challenge our physical understanding of other problems at hand. And with that, I thank you for your time. And if you have any questions, I'd be happy to answer.
Thank you, William. Are there any questions from the participants? When you say here in the outlook that deeper perturbative calculation, do you mean going to higher loops?
That could be an option, but in fact we really looked at those computations to highlight the behavior of that lensing mechanism. So now that we've shown that they don't appear at the same order in the regularization, there's not much use for us to go further, but it could always be an interesting computation.
Mm-hmm. Any other questions? Andreas?
Yeah, I have a question on this average transverse momentum. So your final result is something like 1 over epsilon or 1 over epsilon square poles. And there was a relatively recent work by Ted Rogers, John Wei Chu. They looked at the same quantity and tried to relate it to the Chu-Sturman function. They actually renormalized this average transverse momentum. Did you try to compare somehow to their work? Use the same model actually.
Okay, no, I haven't seen this work at all. I'd be very happy to look at it, yes, to see how they do it, yeah. if you could link it to me, for example, in the chat, I'd be very happy to look at it.
Can do that.
Okay, thank you, William.
Thank you, everyone.
Let's move to the last talk of the session by Simone Rodini, who is going to talk about the energy momentum tensor form factors in QED.
Thank you, Marta. And you should hear me and see my slides, correct?
Mm-hmm.
Okay.
Yes.
Okay, so albeit the title said that I will talk about all the form factors, I will focus on the so-called D term, which in previous talk has been called capital C, so slightly different notation, but still. So brief outline, so some basic definitions that you already saw during these talks. So I will go quickly on them. Then a few words on why the D term matters, and also this should be almost clear to you if you listen to the previous talks. And then I will show the results in QED, that simple one loop calculation, but keep in mind that QCD results at one loop are exactly the same, besides some color factor that needs to be put in place. And these basically are the corrections to all kind of model calculations for the proton or the alpha strong corrections. So, and then I will talk about briefly pressure and shear distributions. So if one works with symmetric gauge invariant energy momentum tensor for massless QED, well, you have your two contributions, naively called the electron contribution, which is related to the covariant derivative, and your photon contribution. Here I put for references the Lagrangian counter terms that should be included to make everything nice and renormalized, at least at the level of the Lagrangian. And we will, if you do the energy momentum tensor in general, as Andreas took at the beginning, you have issues on how you renormalize these operators. You have the mu to epsilon UV, which is the scale to make the coupling dimensionless. So turns out that it would be nice to include a non-zero photon mass in the calculations for a reason that will be obvious later. So how can you include a massive photon? Well, you have many options, but the two most prominent one are you modify your theory using Stackelberg Lagrangian, or you introduce an abelian U1 symmetry gauge symmetry breaking. We went with the latter, so we include the Higgs field. The results are unchanged at the order alpha calculation. The two theories are, of course, different if you go higher order in alpha, because then your extra degrees of freedom that characterize your theory plays a non-trivial role. And for reference, we use R1 gauge, so we decouple the Goldstone mode of the Higgs field, and basically it reproduces the Feynman gauge. So parameterization of your energy momentum tensor, you already saw this, A form factor, the J form factor, C bar, which is the non-conserving form factors, and if you sum over electron and photon, the C bar goes away, and then you have the D form factor, which is what we are interested in. If one take the correction to the vertex of the energy momentum tensor, you will have other, these are not all the diagrams for the alpha, but the other diagrams are tree-level vertex with the energy momentum tensor, and then a Lagrange normalization, which is known. So the like interesting diagrams are these ones. V1, V2, V3 are basically the covariant derivative of the electron that couples to the energy momentum tensor. So V1, V2, V3 is the electron contribution. V4 is the photon contribution. And then you carry out your calculation in the standard way in perturbation theory. So why the D term is important? Well, it is one of the least known global properties of particles. All the particles have a non-zero or possibly zero, but still D term. For non-vanishing momentum transfer, D of T is related to pressure and shear distributions, where D of zero is involved in the definition of mechanical radius or energy radius of your system. So And in some sense, the sign, especially of D of 0, is linked to the stability of your system. Concerning the D term, we do not need to worry about renormalization at one loop, so I will skip all the renormalization details because they do not matter. And if you carry out the calculations, you find that you can cast your D term as a function of tau square, which is nothing else than the momentum transfer, the Mandelstam variable T, positive and normalized with respect to the electron mass. You can cast the result into this double integral form, in which all the dependence on the tau square is at the denominator, and also all the dependence on lambda square is the denominator. And this function looks rather ugly, but doesn't matter really much. And you can plug them in for the electron. You can, with a little bit of patience, you are able to extract a closed form. For the photon, that is not possible. You will end up with some implicit dilogarithmic functions that needs to be evaluated numerically. So if you go to zero momentum transfer, you see that a divergence appears in the photon sector, whereas the electron contribution is finite. If you want to regulate this divergence, you can take a non-zero, the non-zero photon mass regulates this divergence, and of course the divergence is recovered in the limit of vanishing photon mass, and you see that in both cases it goes like lambda or tau as the divergence, so it is inversely proportional to tau or lambda. And if you plot your D term at 0 as a function of the squared of the photon mass over the electron mass, you find that for very small values of lambda, you have a finite D of 0, but the qualitative feature is not that different compared to 0 photon mass, so you have a large D term. Instead, at some point, the D term becomes negative, there's a minimum, and negative D term is somewhat a characteristic of bound states. And then if you really increase your photon mass over electron mass ratio, you basically end up with a complete suppression of the loop contributions. So you basically recover up to some prefactor the 3-level results, and 3-level you do not have any D term. So you consistently find 0. And you can also look at the very large tau square limit that is not very much influenced by the values of lambda square. So I just showed to you for lambda square equal to 0. And you see that it goes like 1 over tau square log tau square over tau square. But it is important to keep in mind for later. And you can plot your D term as a function of tau square. In this case, on the left, you have the zero photon mass. On the right, for the minimum value of D of 0 as a function of photon mass. So this is the minimum of D of 0. This plot is for the photon mass, which minimizes D of 0. And you see that in the former case, you have a change of sign, because here we are plotting the absolute value of the D term. So you have a change of sign of your D term. Instead, in the right panel, you see that the D term is always negative and do not change sign. So you can define in terms of the D term the mechanical radius. If you work with 0 photon mass, this is strictly undefined in QED. But if you switch on the photon mass, no matter how small it is, you find a vanishing mechanical radius. So this, in some sense, could make sense because the electron is point-like, but it is somewhat difficult to assign a meaning to this mechanical radius for a point-like particle. And the fact that it's 0, it is due to the slow fall-off at large momentum transfer, which was that log 1 tau square minus log tau square over tau square behavior. And this is the same for electron and photon, so this behavior is not dominated by the photon by any means. So you can then, once you have your expression in as a function of tau square, even if it is written as a double integral, it doesn't matter. You can take the Fourier transform, and go into position space. For the sake of this discussion, we work with vanishing momentum transfer in the time direction. And you can basically take the definition of what is the D term and calculate the pressure and the shear using well-known relations. And you find that, okay, the shear is well-defined just in terms of D, of the D form factor, whereas for the pressure, you need to include also the non-conserving form factor C bar. So what we find is that in QED, you find a constant C bar as a function of tau squared. Therefore, you find some singular contribution to the pressure in coming from C bar. Thank you, Marta, as a function of rho. Nice consistency checks, von Laue condition, that is check satisfied. And this can be written just in terms of D because of the sum rule for the C bar that is valid for any values of lambda squared and tau squared. Then you can also play the exercise of integrating just the pressure due to the D term, and since separate electron and photon contribution are conserved if you ignore the C bar form factor, we should find 0, and that is also the case for us. So the result seems consistent, and then you can go forth and put the analytic results. Just in this case, just for the pressure due to the T term, you find that, well, of course, the C bar contributes just to the singular part because it is constant in tau squared. And you find that actually, you find also a singular contribution to the pressure, which looks incredibly similar to the C bar besides this double integral of Fi of xy. And you can, if you try to take the limit of rho that goes to 0, you will see that the sum of finite and singular gets you a meaningful result. Then you can play the same game with the shear. You have some slightly different combination, but you see that more or less the structure of the integrals are the same. You have different prefactors, but that is not incredibly important. Another check that one can do is the large distance limit. And naively, you see that, okay, if you look at these equations, you see this exponential of minus rho, so you expect exponential fall-off. But due to the structure of this double integral, the fall-off is lower than the exponential. And actually, you find the rho to the fourth. And these are dominated by the photon, which is okay with previous calculation, with what we saw in the momentum space, in the momentum in tau square dependence, because the photon dominates the low tau square, so the photon should dominate the large rho, and that is the case. And these results were known for a long time and in the literature, just in the asymptotic region, and we reproduced it. You can also look at, once you have pressure and shear, you can look at your forces per unit area, either normal or tangential. And you find out that if you just plot, you find very different plots compared to what you expect from models. You find always positive normal force. And this is due to the fact that you have here in plotting just the finite contribution, then you have a singular contribution at rho equal to 0 that compensate this strange behavior. And here you have the two cases that are really different. If you go to the tangential forces and you plot rho to the fourth, you see that for lambda equal lambda minimal, I remember that the lambda min is the value of lambda that minimizes d of 0. You find a nice and integrable result. Instead, if you go to lambdas equal to 0, you find something that diverges if you try to integrate this object over. So brief conclusions, I was quick. The D term is a fundamental quantity, as we saw during all the talks, at the same level of mass, spin, etc. for particles, so it is meaningful to study on its own. As I said earlier, QED correction to the D of T form factors are, first of all, in principle present also in QCD calculations, so you have pure QED corrections, but these are expected to be somewhat small in the sense that alpha is small, but we saw that in position space, especially at small rhos, you have something that blows up, or in momentum space, d of t for t near 0 is very large. So it is not at all trivial to say that QED corrections for small values of t are negligible. And also the QED results up to color factors are identical to one loop QCD corrections to whatever proton bound state calculation you want to do. And therefore, in principle, are present. Then probably the bound state structure of the proton cures these problems of d of t for small t's, but this is something that should be checked, especially in model calculations. And in general, once you have some knowledge of d of t, you can derive different, from d of t, you can derive different information on your system, the mechanical radius and the energy radius, of which I didn't talk about. And of course, we saw that pressure and shear distributions. So thank you for the attention, and I will gladly take questions.
Thank you, Simone. We have time for questions, so please raise your hand.
Can I ask a question, like Szymanowski?
Yes, go ahead.
Okay, I have a following question. Did I understand correctly, okay, that if you put photon mass to 0, okay, everything breaks up, yes? Okay, so there is no mechanical picture, yes?
Well, in the sense, I mean, you do not have a finite d of 0.
Because I understand that that there is no rest frame in this case for the photon, which is okay massless, yes? And this is the point, yes?
Sorry, there is no?
There is no rest frame for a massless photon.
Yes, but okay.
So this is the main reason why everything okay breaks, yes? Am I right?
No, we are always calculating the form factor for electron states. So this is just the photon. I mean, if I go back,
yes.
If I go back here, we are always everything. I mean, the divergence is due to this vertex in which you have external electron lines.
Okay, but if you would perform the same calculation with photon in external lines, okay, because finally there is a parton distribution inside proton, inside photon. So yes. What would be okay? If, do you have a feeling?
Okay, we didn't do the calculations. I mean, we just focus on the electron external as external particles. Okay. You can find the results in this Behrens-Gassman paper for the total D term. They do not separate between electron and photon contributions, but they separate between external electrons and external photon slices.
Okay. A second question. Those results, okay, do they depend on the way as you are introducing photon mass? For example, okay, you can use the Stuckelberg, okay, mechanism.
Okay. No, the results up to of course first order. So if you stop at order alpha, the results are completely independent on exactly how you generate this photon mass. If you go higher, you have different theories. So you will have different loops also in the loop structure. If you go 2 loops, you will have the loops with your X field or the Stackelberg ghost field. So,
okay. Thanks a lot. Okay.
You're welcome.
All right. So thank you, Simone. I also want to thank all the speakers of the session. We now have a few minutes break at 10 a.m. The next session starts, but feel free to discuss any of the talks of the first session.